Okay, so what I did for all of you, for when you do this, is I didn't want you to have to constantly program all the stuff to put all these elementary flows together. Like you can go back to my previous examples and you can kind of copy and paste it a whole bunch. What I did instead was at the very bottom of this, because of how these live scripts worked, which are live documents worked, um, I went ahead and created this particular function for you. There's two of them. One's called flow. That just is going to plot it for you along or make it a particular grid. It's using the same grid I used earlier. It's always from -2 to 2. If you use something different, you have to not use it. And then I had something called eFlow, which simply is all the different types of elementary flows. And so you just type in flow, and you give a source, sink, uniform, or doublet. You tell it how strong it is and where it's located. It will add it, put it on their grid for you, and you can just add them together. So you don't have to program each one individually. You can just give the strength, you can give its position, and then go from there and you're done. So for example, all I did right here was I have my mesh grid. I have this. I didn't actually need that. I guess I used that for the contour plot. Okay, that's why I needed that. And so what I do is I say, okay, well, psi total, you're equal to a source flow plus a uniform flow. You see that? And what does it pop out? The semi-infinite body. Then I say, okay, well, second one, you're a source flow plus a uniform flow plus a sink flow. And what do I get? The Rankine oval. So I can add these together to turn into other things. And I can do all kinds of things I want to. Like, for example, what's this? Let's try another one. So I'm going to say psi total 3. I'm going to give a, wait a second. I'm going to make a vortex flow. And let's see, what should its strength be? I forgot to put strength here. I'll make it 50. I'm going to add this to a source flow. That looks good. And I can do a contour plot of this. So what is going to happen? I have a vortex flow plus a source flow. What do you think? What do you think it's going to what do you imagine it'll look like? Just think to yourselves this. What does a source flow do?
Flows in one direction.
Flows outward, right? And if we do it in 2D, we'll have to think about it in 2D. It flows outward in all directions. And what is a vortex flow? So if I'm going outward in all directions and I'm going in a circle, what do you imagine that would look like? Yeah, but going outward, right? They're going out and circling at the same time. Well, let's see if that's actually the case. Nice! As a note, there's this discontinuity because of how the vortex flow, actually it's because how the source flow gets created, which really frustrates me. It's just because it's based on angle. So when it goes from 0 all the way back to 180, you have two values that are really close. It is what it is. Let's try getting rid of this and see if I can make it look nicer. I want to figure out how to remove that discontinuity. That looks horrible. Let's try 100. There we go. You see them? Yeah, there is this discontinuity. That discontinuity is simply there because of how I have to define things.
So the uniform flow is just forming it together with like the rod.
That was me adding a uniform flow plus the source flow. And when I put those two together, it looked like the rod.
Okay. And just the source is going to be that rod. Okay.
Yep.
Now it makes sense.
So I'm adding different simple flows together to get something more complex. This is like the flow for if I'm looking straight down at a whirlpool. Or, I guess it should be a sink technically to be a whirlpool, but so it works.
Isn't this like what would happen like on like a winglet, like the end of a wing?
Ooh, I like that. And yes, you would have sort of like a little vortex at the end. Now that kind of moves with it, but yes, you would have something very much kind of like this at the end of a winglet. Okay, but I just want to show you that you're using these things, you add a bunch of them together, and when you do that, you get a more complex flow. In fact, you can get a flow that looks exactly like your airfoil if you add enough shapes together. And how we do that will be what we're talking about next week. We're going to be going into detail about how we can go through that method to get to it. I might give you an absolutely insane example to show it to you because it's awesome. Okay. So example 1. There's some test cases here. And does anybody remember when I talked about circulation leading to lift? Right? Circulation leads to lift. That was a very important thing. And one way we're going to eventually prove that is by looking at a cylinder and saying, okay, if the cylinder is spinning, if you have a baseball and it spins, you can actually, it will have lift. If you spin a baseball fast enough, it will just rise into the air. Now, it's not,
Sorry. Does it have to be in one direction or it doesn't matter?
what direction it's spinning?
Yeah.
Yes, the direction it's spinning matters. It also matters in what direction you threw it. That's how curveballs work and all those other things. I mean, okay, I say curveball. There's a lot that goes into that for baseball. It's not my specialty, but like, for example, if you're doing bowling, if I spin the ball before I throw it, it will begin to go in the direction I spun it. This makes sense. It's going to grab onto the ground. But the same thing's happening to the air. It's more or less grabbing on the air and it'll pull itself in one direction or the other. Now, that's because of Bernoulli and a lot of other things we're learning about. By the way, before we get to a spinning cylinder, let's look at a non-spinning cylinder.